Hi, good evening. So a few weeks back, we made a workshop, actually two workshops for how to prepare technical feasibility studies for broadcast, which includes coverage, propagation, and interference determination for digital television. Now, in the course of that workshop, we have covered some of the propagation and planning tools that are available in the market. So there's one free, which is Radio Mobile, and there are commercially available softwares in the market, such as the digital reception simulator developed by Mr. Komada Junji, and then the other one is Progira, which is quite widely used in the Philippines. Now, for the propagation softwares, the engine that runs inside are the algorithms that makes each of the coverage prediction done by a particular engineer unique. So those are the things that we're going to cover today. So tune in. So now we're gonna talk about the propagation models, the essential ones and the common ones. What are the misunderstandings and when they were introduced. So we'll be covering four of the popular propagation algorithms that have been used widely in some territories, North America, in Japan, in Asia, and in Europe. So we'll talk about the Longley Rice methodology, the Okumura Hata, the CRC. We have the CRC COBLAB or COLAB, and the ITU standard 1546. For the Longley Rice methodology, this one is adopted by the FCC under the Office of the Engineering Technology Bulletin number 69, was introduced in 2004, I believe, and it utilizes the irregular terrain model. So this FCC bulletin provides guidance for the use of Longley Rice methodology for evaluating TV coverage and interference in accordance with sections 73.622, 73.623, and 74.704 of the Code of Federal Regulations. Kindly go to the FCC Code of Federal Regulations webpage and then see about those chapters that I have mentioned. Now, the scope would be the Longley Rice methodology, a radio propagation model used to make predictions of radio field strength at specific geographic points, meaning from point 1 to point 2, and the other points surrounding it, adjacent and opposite to it, based on the elevation profile of the terrain with respect to the transmitter and to the point of reception. So it has to run its simulation with the terrain in consideration. Now we have this topographical map from NASA, which is freely downloadable and has been incorporated in use in the Longley Rice methodology to provide an output based on the irregular terrain model. So pretty basic and pretty straightforward. So the Longley Rice methodology operates from 20 megahertz up to 20 gigahertz. As developed by Miss Anita Longley and Phil Rice in 1968. Now, this methodology requires a computer to aid the user into the generation of the calculation. It's quite tedious to do it manually, so the support of a computer is almost mandatory and essential to the proper use of it. So for the field strengths using this methodology, so in calculation for the analog low band VHF from channels 2 to 6, so that's from 54 megahertz up to 88, to 88 megahertz is 47 dBu. And then for high band VHF channel 7 to 13 in the Philippines, so that's from 174 up to 216 megahertz. The required field strength would be 56. And then for UHF band 1 and band 5, then is from channels 14 to 69. Before it was 470 megahertz up to 890 megahertz. With the new ITU channel allocation, we were left with band 4 only, so that's channel 14 and up to channel 51, and that's 470 megahertz up to 700 megahertz. And then the required field strength would be the resulting field strength based on 64 minus 20 log of 615 divided by the center frequency of the channel of calculation. For the field strength for digital stations, so we'll just concentrate on the UHF. So we'll use from channels 14 to 51 would be 41 minus 20 log of 615 divided by the center frequency of the channel desired. Next is Okumura-Hata. So Okumura-Hata is quite popular. When I say popular, it's a common term that comes out to the from any of the planning engineers, but there are so many misunderstandings about it. So first one is Okumura-Hata is was developed with the purpose of doing the predictions for mobile communications. So for outdoor conditions from 150 megahertz up to 1.5 gigahertz. And then the desired or the effective propagation area would be just within 10 kilometers. So from 1 to 10 kilometers. So it is not really meant for long range coverage prediction and quite suitable for cellular coverage, because the usual range for a cell site would be from 1 to 10 kilometer radius. And if you would want to know more about the Okumura-Hata, it has generated a graph that would show the path loss when it comes to open rural area, suburban, and the metropolitan area. Next is the CRC predict. So most people mistakenly think that the CRC means cyclic redundancy checking. On the other hand, or on the contrary, CRC means Communication Research Canada. So the Canadians developed this, and this model, this algorithm is widely used and mandatory for the determination of coverage and interference within the Canadian territory. So they have come up with their own simulation software. I think it's free, but I've never tried it. I never downloaded it. They call it the CRC CovLab. So it's a Communication Research Canada Coverage Laboratory. Yung meaning nun. And they also have the more portable version, the CRC CovLite. So do look it up, and then if you find the software and you can use it, please inform me and share the software also to me. So yeah, so this algorithm is called the CRC predict. So this program uses a sort of a lower, no sorry, not the lower, but the less comprehensive diffraction model of the ITU. So because if you use the full set of the diffraction model, the calculation is quite heavy for computing and requires more time. So they decided to use a lighter calculation method of the diffraction model. So the CRC algorithm takes into consideration the recommendations of the ITU ITUR P1411 and then ITUR P452. So what is the difference between the two? So the ITUR P1411, the latest version being September 2021. This is a propagation model for short distances outdoor communication from 300 megahertz up to 100 gigahertz, meant for local radio networks, for line of sight and non-line of sight. So which means you have the direct line signal and then the Fresnel zones up to the radio horizon. And then the ITU-R P452-18. 18 is the latest version, which was released last August 2023. This is a prediction procedure for determining interference between stations on the, of course, the surface, in the radio horizon also for frequencies above 100 megahertz. So yun. Plus, this 452 recommendation takes into consideration the aspect of the word, I need to be clear, hydrometeor scattering interference, and the impact of moisture and rainfall to your propagation. So the increase in the volume of water from the rainfall increases the dimension of the rainfall, which impacts certain frequencies of operation. So also, there's a definition of the clean air propagation, which is under ITU-RP 452 also, would be the line of sight propagation, diffraction, tropospheric scattering, ducting, overall prediction model, and then the calculation of loss. And then aside from the clean air propagation model, there's the hydrometeor scatter interference prediction, which takes into account the theoretical basis of transmission loss due to hydrometeor scatter, which means the density of the air and occurrence, persistence of the rain in terms of the millimeter size, the model input parameters, and then the various steps in applying the hydrometeor scatter algorithm, all of which are included in the ITU publication. So just download the standard. So for ITU-R 526-15, which the latest version was released October 2019, this is the recommendation by diffraction. So this standard is specifically enumerating the diffraction model. So the recommendation presents several models to enable the reader to evaluate the effect of the diffraction on the received field strength. The models are applicable to a difference of obstacles and the various path geometries, which means the varying terrain, the size, the bulge, to be used in the calculation of field strength over the path, communication path, which includes a spherical earth surface or irregular terrain with different kinds of obstacle. So when they say the obstacle, sometimes we call it basic communication theory as the height above average terrain. But this one takes into consideration the multitude of these earth bulges being calculated in a computer environment. So diffraction model, so we have the direct line of sight, the reflection, which is the Fresnel zones, and then the knife edge diffraction. So for the knife edge, it's essential for us to know how high is the obstruction that created the diffraction, and then the other one is the negative height factor, which is also, of course, in theory there is this application of the negative height factor, and this is well taken care of by the algorithm embedded inside the recommendation. So feel free to download the recommendation. Next is the ITU-R P 1546-6, which was released last 2019. So this is most reliable of all the algorithms for coverage prediction in broadcasting. This is highly recommended. They call it the method for point-to-area prediction for terrestrial services in the frequency range of 30 megahertz up to 4,000 megahertz or 4 gigahertz. And then this recommendation intended for use in tropospheric radio circuits over land paths or mixed land and sea paths up to 1,000 kilometers of length for effective transmission antenna heights less than 3,000 meters. So where can you find a tower that has a 3,000 meter height, or if it's on top of the mountain, the aggregate height from sea level and then the tower on the mountain. So, and then the method is based on the interpolation, extrapolation from empirically derived field strength curves as function of distance, the antenna height, frequency, and percentage of time, which has something to do with time availability. The calculation procedure also includes corrections to the results obtained from this interpolation, extrapolation to account for terrain clearance, and terminal clutter obstructions. So the details that this algorithm have in order to generate the most detailed coverage simulation and interference determination are the following. First is, there are predetermined coverage curves already that has been performed to aid the user or designer. So you can actually check those propagation curves inside this recommendation, downloadable on the ITU website. So the curves are based on standard 1 kilowatt ERP at nominal frequencies of 100, 600, and then 2000 megahertz interval respectively. Next would be the maximum field strength values on the Annex 2, 3, 4, and 5. Computer-based tabulations contained in Annex 2, 3, and 4. The step-by-step method or the exact procedure on how this model calculates is contained in Annex 6. Designation of the antennas would be on Annex 5. The height of the transmitting antenna, Annex 5 and Annex 3. The height of the base antennas used for the curve, Annex 5 and 4.2 and 4.3. The time variability, Annex 5 and 7. Mixed path method, so we call the direct line of sight, the Fresnel zones, the diffraction, the tropospheric scatter, and ducting. Those are the mixed paths that we take into consideration. The receiving antenna height, or specifically receiving mobile antenna height, which is standardized here. So this is one of the commonly answered question, or answer to the most commonly asked question: what is the standard height for receivers? And it's embedded in the ITU 1546. Next would be the effect of clutter, shielding on the base antenna, the terrain clearance, angle of correction contained in Annex 5 and 11, location variability. So, and then next, correction based on tropospheric scattering on Annex 5 and 13. Correction factor for antenna height difference. So if you change from the 10 going higher, 12, 13, 14, 15, contained in Annex 5 and 14. The equivalent basic transmission loss on Annex 5 and 17. The variability of atmospheric refractive index, Annex 2, 3, and 4. And the compatibility of ITU R1546 to the Okumura-Hata method. So, in summation, ITU 1546 is designed for long-range coverage prediction covering the line of sight and the radio horizon or the Fresnel zones, including the diffraction, the knife edge tropospheric, and also the near field determination of coverage as specified in the Okumura-Hata, which is within the 10 kilometer radius or 10 kilometer distance around the transmitting tower. So I hope you learned something about this explanation about the various propagation models. So I do look forward to seeing you again on my next episode. Bye-bye.